method 1, we assume that the denominator is split into different linear terms. In method 2, we'll allow for a bit more flexibility. We'll say all your terms will be linear, but some might be repeated. So assume that q of x has x minus a to the m in its factorization. So if that's the case, when you build your partial fraction decomposition, you're going to have to include more than one term for x minus a. You'll have to include m different terms. Then include I'm going to have one term with x minus a. I'm going to have one term with x minus a squared, and I'll keep increasing the power of x minus a until I reach the power that is in the factorization of q of x. And then partial fraction tells you that there are coefficients that you could put on top of this that will make it equal to q of x. So let's call them a1, a2, a3. All right, so you should include something, A3 would be funny, but let's put AM, because we're not assuming that there are only 3 terms. Let's try an example. So let's say we're asked to evaluate this integral, minus 3x squared plus 26x minus 20 over x minus 2 squared x plus 3. Then I'm going to use partial fraction, but method 1 doesn't apply because my q of x as a repeated factor of x minus 2, it appears twice in my factorization. That means I'm going to have to apply method 1 with this addendum that says if you have a repeated factor, you need to include more terms for that particular x minus a. So here we're going to take our fraction, we'll need 3 different blocks for it. The first one is x minus 2, second one is x minus 2 squared. That's what this tells us. You keep increasing the power of x minus a until you reach the same power that you had in your factorization. Here we had a power of 2, that means I'm going to need 2 of these factors, one for x minus 2, one for x minus 2 squared. And the third term is going to be x plus 3. That has a power of 1, so I only need 1. And on top, I need coefficients. You could use whatever variable you want. I'm going to keep it simple. I'll use a, b, c again. what we've been doing before, because we have the same term twice, we can't just leave x minus 2 because then the common denominator would just be x minus 2x plus 3. We need to raise it to an x minus 2 squared. So now I need to figure out a way of finding the values of a, b, and c. I'm going to start the same way we were doing for the distinct linear terms. I'm going to multiply both sides by the denominator, clear out the denominators, and then plug in values of x. Alright, so on the left side, I'll be left with minus 3x squared plus 26x minus 20. Now on this side, that x minus 2 here will cancel out with one of these. And I'll have a single x minus 2 left and the x plus 3. Now for the b term, since I have 2x minus 2 squared here, I have two of them, it's going to cancel both. And so the b will only be multiplied by x plus 3. And the c, well, is going to cancel the x plus 3. I'll be left with x minus 2 squared. At this point, I'm going to plug in values of x. We'll plug in 2. It's going to get rid of these two terms. So at x equals 2, I get minus 12 plus 52 minus 20. So that's 20. That's going to give me 0a plus 5b plus 0c. So I'll get that 20 is equal to 5b, and then if I solve for b, I'll get that b equals 4. I'm also going to plug in minus 3. These two factors will become 0 at minus 3. So here we'll get 9 times minus 3, that's minus 27. Is that right? Yep, that's right. Minus 125. I had doubts, it seems so high. It's fine. All right, so then if I plug in minus 3 here, I'll get 0a. Here I'll get 0b. Here I'll get 5 squared, oh, that's why, 25c. So that's equal to 25c, which means that c is minus 5. It don't have a nice third value to take, right? Minus 2 and 2 and minus 3 are the only ones that are going to cancel some of these. So I'm going just take something that's easy enough. So I like 0, so I'm going to take x equals 0. On the left, I'll get minus 20. Then I'm going to get a times minus 6 plus 3b plus 4c. I already have b and c, so really the only value that I don't know in this, the only unknown left is a. So I'm going to solve for a. So a equals minus 20 minus 3b minus 4c divided by minus 6. So minus 20 minus 12 plus 20 divided by minus 6. That's if I plug in minus 5 for C and 4 for B. That's what I'll get. And so the 20s cancel. I'm left with A equals 2. All right, so we found A, we found B, we found C. We're ready to integrate. So I'm going to get A over x minus 2. I'm going to get B over x minus 2 squared. And I'm going to get C over x plus 3 dx. Perfect. The first and the last we've seen before. We even have a proposition that tells us what it is. We have a formula for it. So 2 log of x minus 2. The middle one we don't know yet, so let's do it for real. And then the final one is minus 5 log of x plus 3. What would you do with this one? It looks almost, oh sorry, that's minus 2. It looks almost like a power rule. It's just that the interior is a bit more complicated. So as soon as you see something a bit more complicated inside a function, you should think substitution. So here I'm going to take u is x minus 2, du is dx. And now it's just the power rule. Minus 2 plus 1, that's minus 1, over minus 2 plus 1. And I'm going to plug back x minus 2 for u. What's missing? Right, I'm missing the plus c. At which step should I start including the plus c? Here, 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 here. As long as you have an integral, you don't need the plus c. Here I still have an integral, Oh, no integrals. So this is the point where I need my plus c, and I'm going to keep it till the end, which is right here.